Hi everyone, I'm Zhou from Wuhan National Laboratories. It is my pleasure to present here. The title of our paper is Boosting Cross-Rack Multi-Stride Repair in Heterogeneous Erasure-coded Clusters. With the rapid development of information technology, fault tolerance for distributed storage is critical. Existing large-scale distributed storage systems have introduced Erasure-code to maintain system reliability and reduce storage costs. Erasure-code has been deployed in Google, Amazon, and Facebook. We consider a special type of distributed storage cluster architectures called a rack architectures, which arrange storage nodes into racks, such that all nodes within the same rack are connected via star topology, while all switches are then interconnected via mesh topology. Each coding operating this as follows: Rs equals k date block into n priority block. Any k out of the n-coded block can recover the origin file. For example, for km22, we can partition flight into two blocks and encode them into four blocks. Once a block fails, we can repair the lost block by reading m into reliable blocks and decoding. Although attractive in terms of reliability and storage overheads, Erasure-code incurs high repair costs in cluster, remaining focused on single block fixtures for each stride because it is the dominating case in practice. With RSKM codes, the typical repair process of a lost block is as follows. First, selecting K block called helpers from the remaining K plus M minus 1 blocks in the same stride. Then, a left node which contains no block of the same stride stops the repair block called requester. Notice also to ensure the racket level fault tolerance. However, when we examine existing repair techniques, they are limited in the following two aspects. First, modern Erasure-code clusters organize the node in multiple racks, and the length of the Erasure-code cluster have heterogeneous bitwise. Second, the storage cluster often organize flight in different strides to guarantee data reliability. When a flight fails, we need to repair multiple strides. To exploit the repair brokenness, we further break down the repair time into four parts. The repair costs are evaluated on Amazon EC2 with 4 rack clusters of type T4G small in the Eastern American and Asian. One instance acts as the switch for each rack, and the remaining instances are organized as storage nodes. We use RS22, RS42, RS63 and set the block size is 56 MBs. We then generated a stride and randomly distributed K plus M blocks across the rack. Table summarizes the breakdown. The experiment shows that the clock-rack transmission time T2 dominates the entire repair time, about 86%. The repair cost in each code cluster is largely determined by the cost of the cross-rack transmission. Therefore, we are focused on how to reduce the cross-rack repair time. Given the importance of the cross-rack transmission, We identify two open issues still existing when reconsidering the multi-stride feature repair problem in rack architecture. We first noticed that the repair solution, which, specifies the helpers to read and the requester to stop the repair date, determines the clock-rack transmission time. Feature A shows clock-rack clause, and Feature B, C, D shows the three repair solutions with different clock-rack transmission times. Specifically, the solution in Feature B randomly retrieved two helper blocks from R1 and R3 and stops the repair block in R2. It needs 7 seconds for the clock rack transmission. As a comparison, the solution with the different helpers from R3 and R4 in Feature C need 5 seconds. The solution with the different requests in R1 in Feature D needs 3 seconds. How to efficiently find a near-optimal multi-stride solution remains an unemployed and important issue. We also identified that the random scheduling of the clock rack repair links will prolong the repair procedure. Feature A shows a set of the 4 clock rack repair links. In Feature B, the traditional mass randomly select link, a thought pruning mode for transmission scheduling, and needs 6 seconds. As a comparison, in Feature C, we launch the conjectured link R3 to R1 at the beginning, so it only needs 4 seconds. We further notice that the minimal clock-rack repair time for a multi-stride solution equates the maximum transmission time in all racks, and randomly scheduling clock-rack repair links will make the clock-rack repair time greater than the maximum transmission time in all racks. Our main contributions include: we reconsider the multi-stride feature repair in rack architectures and heterogeneous network environments, and identify the cross-rack link with inefficient bandwidth resources become performance brokenness in repair, which motivates our work. We present CM repair, which generates the repair solution to reduce the clock-rack transmission time and schedules the repair links to saturate the bandwidth resources. Experiment results show that CM repairs reduce 6% to 62% of the clock-rack repair time and improve 28% to 53% of the repair throughput. CM repair can be displayed into generating repair solution and scheduling repair links. Let's start with generating repair solution. In the beginning, we first initiated an optimal single-stride solution for each stride by AZ, which considers the rack architecture, and we choose it to serve it as the cornerstone. After building the initiated multi-stride solution, we employ the grid algorithm to integrate optimals. Specifically, in each optimization, we located the rack Rx with the maximum transmission time Mt. If the upload time of Rx equals Mt, then the repair procedure is broken by the clock rack upload link in Rx. We need to find another valid solution that retrieves no helpers block from Rx. Reducing the download time of Rx is similar. After substitution, the maximum transmission time Mt decreases, and the algorithm finally returns the multi-stride repair solution. We elaborate the design via an example. Consider the repair for three field stride S1, S2, and S3 in fixture. The cluster deployed with RS22 has 3 racks and 6 nodes. Figure A shows the block layout and the time cost between racks. Suppose the block B16, B24, B31 are filled. As shown in Figure B, we can observe that the download link of R1 has maximum transmission time 7 seconds, and 3 solutions choose the R1 as a request. Therefore, the repair procedure is broken by the downlink of the R1. To reduce the download time of R1, we choose R3 as a requester and substitute the solution in Figure C. Hence, the maximum transmission time of the new multi-stride repair solution in Figure C is reduced to 5 seconds after submitting. As mentioned above, randomly scheduling link will make the clock rack repair time greater than the maximum transmission time. The key challenge here is determining the executing orders of the clock rack link. Therefore, our main idea is to move the congested link to the earlier scheduling stage. We set a counter CUI and CDI for each rack RI as the number of a set uplink and downlink respectively. Two parameters reflect the congestion level of the rack. Then, the congestion level of the link Ri to Rj is calculated by equal 1. Then, we sort each link based on the congestion level in descending order. The congestion level of the link reflects the bindwidth usage of the link. The higher the congestion level, the higher the occupancy rate of the bindwidth resources. We elaborate with an example in Figure. Figure A showed an example setup which contains 4 rack and 5 clock rack links. Figure B shows the computing procedure of the congestion level. Figure C shows the execution flow of the 5 links for randomly scheduling, and it needs 7 seconds. For CM repair in Figure D, the most congested link R4 to R3 is scheduled first. We see that the congested link R4 to R3 and R4 to R1 are eventually spread among the repair and do not compete for network resources. CM repair reduces the clock rack repair time from 7 seconds to 5 seconds. For example, 25.6% safely. We run experiments on simulation and Amazon EC2. We launch instance of the type T4G small in the Eastern American region for Amazon EC2. For default configurations, we set the block size to 4 MBs. The number of strides is 15. The number of rack is 4. We choose RS63 as the initial coding. The bindwidth between the rack obeys the uniform distribution across the measurements of the real-world network. We consider the following repair arguments, including conventional repair and easy recovery. We next study the impact of the parameters configured in CM repair. We vary one parameter while keeping the other default parameters unchanged. Picture shows the experiment results. Overall, CM repair incurs the least repair time among the three techniques, when the number of the node, feature A, the number of rack, feature B, the number of stride, feature C, and the coding parameters, feature D change. Specifically, CM repair can reduce 25% to 62% and 6% to 47% of the repair time compared to RR and AZ respectively. We next use the different number of strides and various different issue codes to measure the computation time for CM repair to establish the multi-stride solution. As shown in figure A, the computation time gradually increases with the number of strides, and the overhead is small. Therefore, CM repair only incurs extremely lightweight computation overhead and can be extended into large-scale clusters. To investigate how the block size affects the CM repair, we use difficult block size and calculated the repair throughput. We find that with all techniques, the repair throughput is stable when the block size increases. Overall, CM repair improves the repair throughput by 97% to 115% and 38% to 15% compared to RR and AZ respectively. Finally, let's start make a conclusions. We present an efficient cross-rack multi-stride repair technique. CM repair first crippling search for a repair solution for each stride that reduce the transmission time across rack. CM repair first, it further careful carefully schedules cross-rack link execution order to schedule the upload and download binary resources. We evaluated CM repair via both large-scale simulation and Amazon EC2 experiment and demonstrate that CM repair can reduce the cross-rack repair time. Thank you.